My name is Harideep Nair, and I'm a PhD student at Carnegie Mellon University, part of the NCAL lab. So we have the lab website here, advised by Professor John Chen. I also have two of my co-authors here, William and Agastya. And today I'm going to talk about NeRTCAM, which is a CAM-based CMOS implementation of reference frames for neuromorphic processes. So let's see what that means. I'd like to first start with a bit of background about what our research group does. And so our group's research mainly aims to build neuromorphic processors that leverage the best of biology and silicon. And we call it as brain emulating silicon optimized. And there are two foundational works that our group relies on. One is Hawkins' thousand brains theory, which was part of his very recently released book. And the other one is based on Jim Smith's 10 plus years of foundational research, which includes neuromorphic temporal neural networks, which is a special type of SNNs, and cortical columns and reference frames. And there are some of the references shown here on this slide. So the basic fundamental unit of the neocortex that we focus on is a cortical column. And a cortical column is a complete, in itself, it's a complete sensory motor modeling system that consists of two main components as we model it, agent and a reference frame. Agent can be built using simple feed-forward temporal neural networks, the type of SNNs that I alluded to in the previous slide. But reference frame where it gets more interesting. It involves grid cells and place cells, and it provides a form of memory. And basically, the key component of this reference frame that holds a sensory map is the place cells. And so the question is, can we build these cortical columns in hardware? And a lot of our prior work has focused on implementing temporal neural networks and parts of the agent, compute, etc. But so far, a hardware implementation for a reference frame is lacking. And so we come from a computer architecture standpoint, and we always ask the question, what's the architecture or microarchitecture that can efficiently implement something, right? So in this case, we are focused on the cortical column, specifically the reference frame. So when we think about the reference frame, it holds a sensory map. What I mean by that is that it models an environment in terms of what features are located where and correspond to what class. So it kind of resembles a key value pair information. And when we think about key value pairs, the first thing that strikes our mind from a computer architecture perspective is CAMs, content addressable memory. So the question that we asked ourselves is that, can we implement a reference frame, specifically the place cells, in CMOS using content addressable memory? And that's where we propose NeRTCAM, which is basically, it's not only a storage that involves storing triplets, which consists of features, location, and corresponding class IDs, but we also have some inference and prediction logic around it that's more biologically plausible. So let's see more details on that. NeRTCAM stands for Neuromorphic Reverse Ternary CAM. And if time permits at the end, I'll get into what a reverse ternary CAM is. But in the interest of time, I'll focus more on how it operates and what are the key components. So as I mentioned earlier, it stores each entry in a NeRTCAM stores feature location class triplet. And apart from storage, the two key biologically plausible operations that it performs is predict and infer. So predict is when you're given a feature and you want to predict what location it may be at and what classes might it correspond to. For inference, given a feature at a particular location, you want to infer what are the classes that are consistent with that information. So let's take a look at a brief example here. So I have three objects here that are composed of three types of features located at different places in the grid. And the specific configuration of these features make what the object is, the uniqueness of the object. So this would be stored in a CAM as follows, where you have the feature, location, and class information. So imagine an agent trying to navigate around this object where, let's say, the first feature it observes is a triangle at 1,3. And if you look up that information in the CAM, you'll get all these matches. And you'll say that, okay, so this seems like it could be either class 1 or 2 or 3. And suppose it sees the circle at 2,1 after that, and it'll see these two matches. And at that point, it will realize that, okay, so this is not class 3. Now it can be class 1 or 2. And the last feature, let's say, if it sees a star at 3,3. So if you notice, there are two instances of star at 3,3, but it'll provide a match only on this one because every time it sees a new feature, it remembers what it has seen previously. So it's only going to look up that feature in the set of valid classes at this point. Because 3 was already invalidated, what you have is class 2. So it has successfully inferred over a set of sequential samples that, okay, so the object that I'm looking at is object 2. So this is just one instance of how an inference operates. So in order to implement these operations in a biologically plausible manner, we came up with a set of macro operations or commands that the agent can provide to the NeRTCAM, which sits inside the reference frame. And these are clear, reset, store, delete, predict, and infer. Clear and reset are pretty self-explanatory, but I've shown store, delete, predict, and infer in this sort of flowchart here. So if you start with store, we first check if an existing match is already present. In that case, we don't need to store it. So that raises an error and goes back to the initial state. But if it doesn't, then you just store the data and set the corresponding valid and empty bits in the CAM. For delete, you perform a similar match check, but it's reversed. If it exists, then you go ahead and perform the delete as usual. If not, then raise an error. In terms of predict, you first determine whether what type of predict is, because in our system, you can predict a location given a feature, or you can predict a feature given a location. And in both cases, it will also predict the corresponding classes. So for predict, we also have some pre-processing stage where you can append some bits to a vector where the amount of fuzziness can be controlled, or some of the bit vectors can be marked as don't cares. And that's where the ternary aspect comes into play. But that allows us to perform partial matches. So given just a feature, you can look that up and get the other missing part of the vector, which is the location and class, for example, right? So that's the pre-process stage. And then you can perform a potentially fuzzy lookup with a fuzziness control and return the valid set of output. Similarly, for infer, you have a similar pre-process and lookup stage. But in this case, if you find a match, you have a specific process that updates the valid bits of the classes, because as seen in the previous example, we want to remember information over time and sort of narrow down the possibilities for classes over time. So that's done through a specialized validates step. So now with these commands, the way we implement NeRTCAM is that it consists of 4 main components: pre-process, which takes in the input vector and generates the don't care mask, which allows us the partial lookup. The input vector consists of 3 fields, each field for location feature class, and each of these fields are one hot in themselves. Then you have the main NeRTCAM memory, which holds these entries. It takes in the don't care mask and the control commands and generates the output. But the other component is the state machine, which actually takes in these agent macro operations and converts it into internal operations, because our memory is, it directly takes in the internal operations that correspond to lookup and validate, for example, as I will show later on. So once the state machine generates the internal operations, the NeRTCAM takes all these input vectors, the don't care mask, and the control commands to generate the corresponding memory output, which could consist of all the set of possible features, locations, and classes. And finally, the prediction map is a component that we have to sort of compress the output. because if you have multiple possibilities, we want to compress them into a k-hot single vector. And this can be done for each of these three fields. And this just shows the memory module here, which consists of data, valid, and empty bits. Now, the state machine that we use to convert the macro operations into micro ops, it consists of 6 internal micro ops. So there are a few that correspond to the macro ops, but the way we generate these micro ops, for example, for store or delete, is that the first thing you do is a lookup, which can be a fuzzy lookup. And then you perform a reset because during store or delete, you don't want to tamper with the valid bits of the classes. It's useful when you're performing predict or infer. And then on a success, you perform the operation. On a failure, you just stop with the reset. But for infer, if it's a success, you just look up and validate. So validate is the internal operation that gets the valid bits of the classes set appropriately. But the one interesting aspect we perform here is that on a first failure, if after lookup you don't find a match for infer, you don't give up. You perform a second lookup because we want to account for the scenario where the agent has been looking at a bunch of observations for a particular object and has suddenly switched to looking at a different object. So that's what we call as a context switch. At that point, it performs a second lookup, and then if it's a success, it performs a validate and moves on. If not, then that ends up as a failure. And predict is pretty simple because you can look up and get the match that's closest to the lookup that you're performing. And so what we've done is we've implemented all these components in RTL. And currently, as our first baseline implementation, we are modeling or emulating the storage using flip-flops. And so we are using ASAP 7 open source PDK, 7 nanometer PDK for our post-synthesis results. We use a 100 kHz clock for more kind of real-time operation. And we have swept across different number of entries, sizes for the CAM, going from 64 to 1024. And each entry in this example stores 165 bits. And this configuration is taken directly from one of Numenta's baseline work that uses MNIST as an example for sequential kind of biologically plausible inference. And what we notice here is that when we go to, for example, the largest size here, which is close to 1,000 entries, it takes in about 400 milliwatts power. And notice that this is with flip-flops. So there's huge optimization potential for this. And the interesting aspect is that this just consumes, even the largest size CAM that we use here consumes just about 0.1% of typical mobile SoCs, because we want to target like edge computing and typical mobile SoCs that are where area dominates more from the memory aspect rather than the compute. There's a lot of potential for stacking multiple of these CAMs. So relying on the MNIST evaluation that the baseline work has done, there are a few interesting aspects about this. One is the ability to learn with arbitrary sequences, where Numenta has shown that a network that kind of models the grid cells and place cells can outperform significantly the other more deep learning oriented algorithms. But for few-shot learning, what they have observed is that with just about 5 training samples per class, you can reach up to 70%, and with about 20, you get to 80%. And in both these scenarios, the KNNs and LSTMs perform pretty poorly. And if you kind of translate that to NeRTCAM, just about 500 entries can outperform KNN and LSTM in about 200 milliwatts of power and 0.08 millimeter square area. And what we observed is that about 10 out of 25 sequences per digit can result in successful inference. In terms of hardware breakdown, the RTCAM consumes majority of the complexity, which is as expected. And that's why there's huge potential for optimization here, as I'll mention in the future work. And then it's followed by prediction map, just about 10%, and state machine about 7%. The pre-process stage, seems pretty negligible in terms of complexity. So to summarize, in this work, we kind of took our first attempt towards CMOS implementation of reference frames, and we suggested a CAM-based building block for that. And we noticed that a sequential inference of MNIST can be performed in a few hundreds of milliwatts power with less than 0.1% area for a mobile SoC. And it leaves potential for cascading multiple of these CAMs for scalability. And in terms of future work, the first immediate aspect is to integrate specialized circuit level TCAM cells to actually model the memory, which means the 80+% of the complexity can be hugely optimized. This work just serves as kind of like a first baseline proof of feasibility for implementing reference frames in CMOS using CAMs. And then we want to focus on building the other components of the cortical column and kind of start creating a complete system with multiple cortical columns, including cross-cortical column voting to create a more like a cortical column computing system in CMOS. With that, I'll be happy to take questions. And yeah, I have a lot of backup slides, so feel free to ask questions.